Hi everyone. I'm going to present today the work that I've been doing with LaunchPad on the representation of a Mozambique channel trough in the CMIP6 models. So just a background on what MCT is and why it is important. So MCT is a cyclonic circulation, a low pressure area in the Mozambique channel, and it is known to be generated by the dynamical adjustment of the easterlies from the Indian Ocean over the topography of Madagascar. And it stays on the path of the South Indian Ocean convergence, so it could affect the Southern African rainfall. From previous studies, models with low topography over Madagascar tend to have weak MCT and thus excess rainfall over Southern Africa and deficit in Madagascar. And the mechanism is that the MCT tends to bring back the moisture in the Mozambique channel into the eastern part of the channel rather than bringing the moisture directly into Southern Africa. So the two figures I'm showing here are the main rainfall anomalies in two experiments by flattening the topography of Madagascar on the left and by removing the topography of Madagascar on the right. So flattening or removing the topography led to excess rainfall over mainland Southern Africa and deficit rainfall over Madagascar. Again, another previous study by analyzing the composite of weak and strong MCT years in the ERAint interim data shows that for strong MCT years, there is a tendency of having less rainfall over mainland Africa and excess rainfall over Madagascar, and vice versa for weak MCT. And the MCT is actually associated with the most convection over the channel in that study. So based on those two previous studies, the aim of this work is actually to investigate how the Mozambique channel trough is represented in the CMIP6 models and to analyze if there is any link between the MCT itself and the simulated rainfall biases. The figure I'm showing here on the right is the 50 hectopascal geopotential height in the models and in the ERA5, which is down here. So MCT is the low pressure area, the blue pattern within the Mozambique channel in the ERA5. And as you can see that the models actually have a different representation of the not only the low pressure area over the Mozambique channel, but the geopotential height itself. By looking at the MCT index, which is the area averaged of 850 hectopascal vorticity during JFM in the southern Mozambique channel, we have this paragraph. So the red is the ERAint interim and the blue for the models. Overall, the models kind of represent well the MCT. The values are reasonably well, apart from a few models like the BCC, the CESM2, and the 2GIS models, which are showing relatively low MCT index. And this MCT index, by the way, is the index that we use for the auto assessment with a ESM-VAR tool. So what I'm going to do for the next couple of slides is to look at the characteristics of the MCT. One on the formation of a vortex, which is characterized by the topography of Madagascar, the upstream winds, which is the wind east of Madagascar, and the static stability. And also look at the maintenance of a vortex within the channel itself on the lee side of the island. So first, let's look at the formation of a vortex. We say that it is due to a dynamical adjustment of the easterly wind flowing east of Madagascar. So one way to characterize that, it's the Froude number, which is given by the ratio between the mean upstream wind velocity and the Brunt-Feiseler frequency and mean topography over Madagascar. So different dots here represent different models. The x-axis is the Froude number, and y-axis is the MCT. So as we can see here, that the 2GIS model here with relatively low MCT, the Froude number for one of them, which is a GIS 1H, it's not completely different compared to the other models. However, for GIS 2-1G, the Froude number is less than 1, suggesting that the flow is actually blocked in that model. Now, if I remove these two models and look at the correlation between the Froude number and the MCT intensity, there is a correlation of 0.46 between the two variables. So we also looked at the different component of the Froude number, the topography and the static stability, or represented by the Brunt-Feiseler frequency. There isn't actually a large difference because the range of the topography is between 200 and 280 meters. But one thing that we notice here, that the BCC model is one of the models that have low topography, whereas the 2GIS models have high topography compared to other models. And in the Brunt-Feiseler frequency, there isn't really much discrepancies in the models. And by the way, the red diamond, is for the ERA5. So what we did is also to look at the profile of the upstream winds at different latitudes. So that's the mean of the vertical profile of the mean wind from -5 to -30 east of Madagascar. So there is actually weaker wind in the GIS 1G model, this one, and in the BCC, whereas the maximum wind is slightly shifted toward the north in the CESM model. For the models with strong MCT, they do not show particular strong wind compared to ERA5. So what we see so far is that models with strong MCT, they do not show any large differences in the Froude number, topography, or the upstream wind, whereas in the models with weak MCT, we saw that either there is small Froude number, small Froude number, or a blocking, or low topography or weak upstream winds. Now let's look at the characteristics of the vortex within the Mozambique channel itself. This figure shows the vorticity profile in the MCT area. Again, in the ERA5, the vortex is overall extended up to 500 hectopascal. For the weak MCT models, that vortex is either weak, or like in the GIS models, or shallow. It goes up to around 600 hectopascal. Now, if we look at the divergence in that MCT area, within that MCT area, we saw that the strong MCT models tend to have strong low convergence, which can extend about 800 hectopascal. So let's say, for example, the EC Earth, we have a very strong low convergence here. By the way, convergences are represented in orange or brown and negative values. So this ERF has very strong convergence, same as other models, whereas the weak models either show relatively weak low-level convergence like the BCC, or low-level divergence. Also, we looked at the Vorticity budget. So down here it's the ERA 5. In the ERA 5, the vorticity tendency is actually dominated by the vertical advection at low level, which is in red here, and stretching and tilting terms. So these are really large, and please note that I'm not using the same scale here because in the ERA 5 the scales are quite large, whereas in the models, in all of them, the vertical advection is relatively weak, but the budget is dominated by the stretching and tilting terms. Now, if we look at the weak models, like PCC, it still has the stretching and tilting term, but the CESM and 2GIS models, the stretching term is actually a sink, not a source. So what we have so far is that models with weak MCT tend to have shallow extension of the vortex in the vertical, divergence or weak surface convergence, or low-level divergence or weak low-level convergence. And the vorticity budget in the models are dominated by stretching and tilting terms, whereas the vertical advection is also important in the ERA 5 reanalysis. Now, if we look at the rainfall bias in the models, so the map on the left here shows the ensemble mean, the bias in the ensemble mean. This is actually a bit different from the usual CMIP ensemble mean bias, because the wet bias is strongly extended toward Madagascar, and the dry bias over Madagascar actually seems to be decreased or becomes positive in some of the models. Now, if I take these two boxes, one over Southern Africa and one over Madagascar, and look at the biases, that gives me this paragraph here. So the red is the bias over Madagascar, and blue is the bias over Southern Africa. And we can see that most models have large bias, positive bias over Southern Africa, except for GIS, but also most models have large bias, wet bias over Madagascar. Now, if I put these two together, so this is the rainfall bias, this is the CMIP 6 MCT. There isn't really any link, the link that we show in the previous study. So the models show high positive rainfall biases over Southern Africa, regardless of the intensity of the MCT. So let's take an example here, ECERF. ECERF has a very strong MCT, but it still has positive bias over Southern Africa and positive bias over Madagascar. So the link between MCT and the rainfall bias isn't really represented here in the models. So what it is, I looked at the vertical motion over the Mozambique channel. So this figure shows the omega cross-section in the MCT, and we see that there is an uplift at the center of the vortex, which is kind of relatively weak in some of the models, and also negative. So there is like a sinking motion in the weak MCT models, and the weak MCT models like the PCC, CSM, and the 2GIS, But also one thing is that there is an uplift over the channel, which is much stronger compared to VERA5. So this could explain actually the large rainfall over the channel itself, extended toward Madagascar, because we have this strong uplift, strong moist convection over the channel. So in summary, for the MCT, most models depict a reasonable MCT intensity. There is also a significant correlation between MCT and the Froude number, which emphasizes the role of the topography, the role of the topography, the upstream wind on the formation of the MCT. The vorticity tendency in the models are dominated by the stretching and tilting terms, whereas vertical advection is also important in the reanalysis. And models with strong MCT tend to have strong low-level convergence in the Mozambique channel area, whereas divergence is seen in the models with weak MCT. If we look at the link between MCT and rainfall, the MCT rainfall dipole link over southern Africa is not present in the model. And as I said, the large uplift and low-level convergence in the MCT area could actually mask the impact of the MCT vortex, leading to excess rainfall in the channel. And I will end there. Thank you.